It's 4:05, so I know some of you want to take the train to Zurich or to wherever. We need to try to finish for 5 o'clock. I have one more thing that was on the program that I care to show you. And then probably we can open it up to general questions, okay? I'll take up this opportunity. There was one question here from the student here, reading some NetCDF data, so the typical data from atmospheric science. And there's only two, in his file, there are 2D and 3D data fields. However, in the ParaView interface, at the moment, he could only see the 2D data. And to do an isosurface of, what is it you wanted to do?
Cloud ice.
Yeah, cloud ice, etc. There was no data available. This is because by design, the NetCDF reader in ParaView only reads the 2D data or the 3D data, but not both of them together. It's probably a decision made to save memory initially. So no problem with that. Just get 2 copies of the reader, one of them for the 2D, one of them for the 3D. Okay? And you will not consume extra memory. It's just 2 separate things. And in that case, you can mix 2D visualization and 3D data. And there will be many file formats around that allow you to do mixed type of topological objects. It's no problem. If you don't know the solution of, if you don't find the solution of by looking, just ask me via email. This was an easy case. All right. This should be pretty short. I'm going to talk about Qt and VTK. So why? Motivations. Integrate VTK with PyQt in Python and making mini apps. Simple for demonstrations or for your personal thing. You don't need the whole ParaView thing, which is very, very big. You just need a simple interface, and this would be a way to do this. I just said that ParaView is actually very big, and there's probably only 5% of the ParaView functionality you need for your specific project at one point. So make it a reduced graphical user interface. Another one is, we've said it already, not all the VTK functionality is visible in ParaView. However, if you write a VTK-only Python script, then you have the full VTK, and you add to this your little graphical user interface, couple of buttons, a couple of sliders, and you're done. So this is what I want to show. The starting point is a tutorial that I found by just looking, by just asking Google. Here's the address. It's done very nice. So thanks to this anonymous author I've never met, but this was the inspiring start point for my thing. Let's look at a typical VTK Python pipeline. That example would have a reader. So in this case, the VTK block, multi-block plot 3D reader. An outline. This is done to get the bounding box of volumes. A mapper, an actor. Then we have here a threshold filter to select appropriate points. The case of glyph is a little bit more advanced in the sense that glyph takes a couple of input. One of them is called the source, the other one is called the input. What does the glyph vector do? What does the glyph mapper do? it, in this case, does a little arrow at each grid point. This is typically used to show velocity fields or any vector field. We're going to use threshold because we don't want to see all, we don't want to put a little arrow on all the vertices, otherwise we'd have too many on the screens and it would be a big mess. So the source to the glyph map filter is the little arrow. That's the geometric object we want to replicate everywhere, so that's the source. And the input is the grid itself, in that case, the grid at a reduced resolution because we are thresholding. Then we have the mapper, an actor, and then the typical renderer, render window, and render window interactor. So that's basically the skeleton of our VTK pipeline. And this will be what we do. We add a couple of actors, the glyph actors, which are the little arrows here. We add them as actor, and then the outline is the bounding box right here. We've seen this data set already this morning. It's part of the normal distribution. You can execute this as a standard Python script using vtkpython. And this would be the syntax. If you're using Python 3, you open your file, your Python file, you read it, and you pass this to the exec module. So this would be the starting point of building a mini app. Have a simple VTK Python script which you can, which is a working pipeline, and you can demonstrate. Let me show it to you, and I will distribute. So the original examples are at this GitHub address which you can find, and then I will distribute the new examples I have made. I forgot where, Qt, there we go. There we go. So 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, those are the 5 different steps of this constructing the pipeline. Let's run it with VTK Python. VTK Python 0, 0. Thank God this is working because I have enough problem fixing everybody's computer here. So there, a simple pipeline with an interactive viewer. I'm done with that. Quit this. Second step. To embed this into Qt, we need to make this application a class. So we're going to do several things. Transform the class into a Qt widget, embed it into a normal PyQt interface. We'll have to change the window interactor to become a Qt VTK render window interactor. Instead of doing interactor initialize, we're going to move this to the Qt interactor responsibility, and we'll encapsulate that into a Q frame. So the original scripts I have found on the web are designed for Qt 4, version 4. They're probably a little bit old now. We've switched to Qt 5 for quite a few years now. I only have Qt 5 installed on my laptop, so I had to make them work for Qt 5. This is the job I do, and it was actually pretty simple. So instead of importing the VTK Qt4 module, the syntax changes to Qt5. So on the left side, you have Qt4. On the right side, Qt5. From PyQt4, instead of including Qt core, which has actually Qt GUI, which has everything, Qt widgets have been now separated as a special module, so you include it like this. The Q main window class, instead of deriving from Qt GUI, now derives from Qt widgets, etc. So you see, it's just a simple replacement of some of the key class names, and you're good and going. Now, making your own Qt interface. I don't think it's so complicated. I myself, I am by no way an expert. I just followed the online tutorials on the web, followed a couple of examples, and I got it working. So this would be the QDesigner interface, where you add a Q widgets, a Q frames, a couple of labels. So there is my slider. There's a spacer. There's here something that we will use for labels. And over here is the Q frame, where we will embed the 3D window. And the final output will be exactly this. A very simple, that's what I promised, 3D window, one slider to change the threshold, and then here we'll print some values later on. So that's the final product we want. And then of course, we are free to populate that with a few more items in the menu. So using my particular installation would be using the designer executable from the bin directory. This would have to be dependent on what you have installed on your laptop. And then we need to attach the slider from the Qt side to a class method on the VTK side, and you'll see the examples. There are no more than half a page, or maybe at the maximum a page of code. It's really all pretty simple for this mini tutorial on Qt. So the slider itself, we define a class method called setThreshold, where from the value given to us from the Qt side, we get a floating point value. And this threshold by upper, this is the class method from the VTK side. So you basically have the VTK threshold point filter that has its own interface and its own set of commands. And you need to find the correspondence between those C++ commands and the Qt side. So threshold is the object on the VTK side, which I have declared. And as we've learned all day long, to actually trigger the execution of the pipeline, we do a render window render. So this gets, we justify here with this render command we've seen all day long. So the demonstrations. So really, yeah, that's all there is to the presentation slides, which I will give to you in PDF. Let's go through the different passes of this. So the 0.1 version we've seen. Here, this is nothing else than transforming the same pipeline as before into a Python class. So it's basically adding an init method and a start method, and then the rest is exactly the Python, the VTK Python script taken and shifted into the class definition. let's look at the source code. So here's version 0 of the pipeline. Exactly like I said, a standard VTK pipeline. Import VTK, a reader, a renderer, the outline filter, etc., the threshold, the glyph, the mapper, and at the very end, the interactor start, and we're done with that. This would be very much parallel to what ParaView would give you as a Python script. First step, you make that a class. So we've basically shifted everything by 4 spaces with a couple of definitions here. So this becomes a class, a Python class. Here we're not talking about Qt yet, but this has become a Python class which makes it easier to then include into bigger project. The class is called glyph viewer. Nothing else has changed. At the very bottom, I have a start method to start the interactor, and then a definition of main to get the class started. So here I declare an object of type glyph viewer, and I start it. Okay, that's my second iteration. Let's look at the third iteration, which is O2. Aha, I am now inside the Qt world. Same thing, my 3D interactive window. This is not active anymore. I mean, the Qt side is active, but it's not connected to anything. But I'm making progress. I'm inside the Qt window. Let's look at our source code. It's number 3, or number 2, actually, because I'm a good computer scientist. I start everything at 0. Step number 3 is file02, import VTK from pyqt5 echo. I start with the Qt widgets, and my class app now derives from Qt widgets Q main window. Most everything else stays the same because at this point I haven't connected the Qt side with the VTK side, but I have designed my user interface using the designer application, which I open here as a UI file. I create in write mode a glyph UI Python code, which I compile with the Qt UIC compiler. Basically, from the description of the user interface widgets of Qt, I automatically compile the Python code, which will serve as a module. So let's look at it here. With this particular Python code, which I have compiled into my that particular name, I can now, at the very top, I'll show you where it gets included. Over here, okay. I import that Python code, and from here, I have the description of my objects. The last, for this exercise, actually, the last thing we do for this demonstration is get the threshold slider object, gets its value, and every time the value change, which is a standard Qt event, gets raised, we can connect that to the VTK widget. Otherwise, I don't have particular things to highlight in that example. Yeah, except the fact that we've added the setThreshold class. I get the new value given to me by Qt, and I feed it to the VTK class object threshold by upper. And this will be the final thing here. Connect with the slider. There is my 3D window, and I should, there we go, be able to interact with my visualization. So I've got a really trivial user interface. I just have a slider and a window. It actually makes a big difference. I have people for which I develop some visualization pipelines. They don't want to hear anything about ParaView, and it's way too big. I want a simple thing, couple of buttons, one open menu, that's it. So that's the solution. I want to show an example of this in my project directory, NVIDIA, I believe. And it's this one, I guess, vtkpython. No, it's not. It's probably viewers. I believe it is, yes. This is an example from one of the big visualization projects that has occupied me here at CSCS for several years. It's the group of ETH Zurich biomechanics on the Angerberg campus. They're doing simulations of bones, real bones, which are, of course, passed through a scanner. The geometry is built, and then stress and resistance computations are on the bone material is done with respect to those implants, so the screws and the plates that surgeons put on your bones when you have broken bones. This was a simple demo that I wanted to do to show 3 different renderers, the standard OpenGL. I don't know if you can read the standard OpenGL renderer, which is this, the NVIDIA optics renderer, which is another library for very high performance rendering, and then the other alternative is Osprey, the NVIDIA CPU-based rendering ray tracing. So the idea here was to do ray tracing with shadows. Did I get my words confused? So optics from NVIDIA and Osprey from Intel. Those are the 2 libraries I wanted to compare. So here's my standard OpenGL renderer. I can click on shadows. It doesn't do anything. Let me switch to optics. There we go. I now have shadows. Okay, so if we look, for example, deep into this material here, this surface, if I turn off the shadows, you see we lose a lot of perception because of this very complex geometry. So there I have the rendering of this mesh in real time with shadows using the NVIDIA optics library, which is available, let's say, without any difficulty through the standard VTK interface. And then Osprey does the same job, more or less. I have a little initialization cost, as you could see, but here I'm doing real-time shadows again with this geometry. Perhaps the intensity here of illumination is slightly different. This is something you fine-tune then at the end. So back to optics, which gives me the fastest rendering. And then I have a couple of options here as far as the quality of my rendering. So maximum frames, samples per pixels. I can still here go full rendering, and here adding additional ambient samples there. So this is the example really of a Qt-based VTK Python pipeline for something really simple to demonstrate to my clients the possibility of having multiple interfaces with the rendering pipeline. So if you are interested in making like this mini apps, Qt-based with 3 buttons, 3 sliders, a couple of Boolean switches, this would be the way to do it. I've installed the PyQt standard module from Ubuntu here on my laptop. I've toggled a switch in the VTK build to enable the Qt rendering widget, and that was it, really. So it's nearly the traditional compile of VTK. And then in about half a day of looking through the web, learning the basics of Qt, I could get that going. So it's really not a big expert development. There we go. As printed on my screen here, I have optics renderer path, Osprey renderer path, etc. What does this mean? It means that all of this is implemented by something Kitware has added to their rendering pipeline, which is really the possibility to do multipass rendering, and there are different types of renderer that you can add to those multipasses. So for example, the depth peeling that we saw earlier this afternoon, it's one type of a rendering pass. And then you have several others which you can mix, not in a random fashion, but you can assemble multiple passes. That's what I mean to say. So the optics pass is just one example of such rendering. Good. That's where I wanted to be. 4:30. I'm not going to close with showing off new things because too many new things, right? And I want to open it up to just questions in general about ParaView and VTK and rendering libraries and so forth. And hopefully you have some questions that are more or less general for everybody. To somebody, yes, Peter, right?
Yeah. Well, yeah, this thinking. 30 seconds.
Yeah, that's fine. Yeah. In general, because this is the first time I present VTK in this particular fashion. Are the things that I'm mostly interested in the things you didn't like, because this would be valuable feedback. The things you like, I'll just keep doing them again, and I'll improve on that. If you're more comfortable by sending that sending your comments to me via private email, please do so. I would really appreciate your feedback. Okay? Yeah?
Batch processing.
Yeah, batch. Oh, that's a very good one, actually, which we didn't do. Batch processing is easy. Okay, I'm done. No, just kidding. It's part of this iterative process of refining the Python script which ParaView will give you. It's usually, let's say, 10, 20 lines of additional code I need to put in the Python script to enable the batch mode. I'll give you two examples. One of them is we've loaded additional plugins through the menu, Tools, Manage Plugins, Load Plugin. When you do that, the plugin is active on your interactive session, but the Python script does not have a record of that. Okay? So the command is, you have to learn it once, it's called load plugin with the name of the plugin. So you put that at the very top of your Python script if you want to run batch. Because when you run batch and you submit your job to Piz Daint, it's going to assume the default configuration of ParaView. So loading the plugin would be an example. Then looping through time steps would be another example. Defining the file names, because usually if you save images to disk, you go through the graphical user interface, open file, you type the file name, and you're done. That command, I believe, if I recall correctly, called save screenshot, is not included in the ParaView script, which ParaView automatically saves for you. So there, those are a couple of examples. There, some of them aesthetic, some of them important, like the load plugin. If you fail to do that, you would. So the process is have ParaView save a Python script for you. You will customize, perhaps edit that file, that script, to make it nicer and to do some fine-tuning. You will reload this Python script in an interactive session to make sure it works. When it works, the same Python script, which is by default saved to on your desktop side, on the client side, you copy this to Piz Daint, and you launch an S-batch job with pvbatch, which is the name of the executable for ParaView, and pvbatch reuses your Python script like this. If you forget the load plugin, it would say the first error, that command is not known. And you'll have to think, oh, wait a second, that command comes from the private plugin. You'll need to add the command. And if you have trouble with that, that's why I'm here for, to help you fix those little problems. And then the rest is really, really simple, as we've demonstrated already this morning. They are usually, the Python script are usually independent of the number of tasks available. This is why you can develop a Python script. You can fine-tune a Python script using low-resolution data on your desktop, using a single task, single GPU, etc. And then when you're ready to move to your big data, you take that same Python script to Piz Daint, you allocate a multi-node job, and that script runs without any modification. There is actually another point which is very important. In ParaView, when we build the pipeline, very often we add something in the pipeline and we click apply. That command apply doesn't exist in the Python API. And you will, at times, have things that are completely wrong in your batch computation, perhaps a completely empty window, or a range of numbers that's not right, which strangely looks like it's between 0 and 1, which would be a default, whereas your scalar data has a different scalar range. Why is that? It's because nothing actually clicked, there was no substitute for the apply button in your Python script. Fortunately, that command actually exists. It's not called apply, it's called update information. So this is sometimes some of the fine-tuning you need for a batch mode computation to take place correctly, is that you need to mimic the incremental buildup of the pipeline, which is done one filter at a time, then you click apply, you add another filter, you click apply. If you, in your Python code, you say sphere, like we did earlier, threshold point, if you don't apply it, it would use use default values. If you say I want 1 every 10 points, update information, then the next module in the pipeline knows what you intend. Okay, so those problems are easy to detect. It's usually a window that's completely empty, an image completely empty, or values that are 0 to 1, or the standard defaults of some modules, and you must think, aha, something was not updated with the real data. Because recall that the pipeline execution is triggered from the bottom, from the renderer. But if some of the intermediary metadata has not been set up correctly, it will not know what your default values are. There, that's more or less the 3 things I can think of. It's independent of the number of processors. That's pretty much a given, unless you actually maybe use a scaling of the column map based on the number of processors or something like this, but this would be a rare case. Loading plugins, looping through time-dependent data, that's not included. And then some of those update information commands which you apply on the Python object to make them set their default to the appropriate values. That's, on the top of my head here, the only 3 things I can think of. Okay? Of course, yeah.
What about output of images in vector graphics formats?
In what form?
Vector graphics formats.
Okay, so you can output in. I'm not very expert on those, but there is encapsulated PostScript. There is SVG. There is X3D. There is web. You can output your data in WebGL format. So you have you have 2 somewhat different menus for output in ParaView. You have the save snapshot, which are really the image formats, and then you have export scenes. And in that export scene menu, perhaps I can just put it up, and we could look at the options we have. If I do ParaView like this with a standard source, I have, yes, export scene And the choices are, okay, EPS, PDF, SVG, POV, VRML, WebGL, etc. Now, still for some of those, perhaps EPS, the last time I looked, the EPS was actually a snapshot embedded into some PostScript code, which is not what you're looking for, okay? This was the last time I looked, probably a year ago, if not more. There has been some recent development with vector graphics. I would have to verify again what exactly gets put out. And there might be some limitation, maybe not all objects are being converted to true vector graphics. This is something to try, okay? I don't have the exact answer there at that level. I will perhaps bring up to the screen a script to illustrate the last point I have made. This would be, I think, a lot more useful to you. I'll look at my biomedical project here, because that one is a place where I do a lot of those. There is the last one, more or less. This is what I mean. No, let me get yet another one. Grep load plugin py. I don't have one. Okay, never mind then. Here is a Python script. Getting a random window, we know this. Using an HDF5 reader, we also know this. And there is a command, update pipeline. And there's another one, update pipeline. And another one again, update pipeline. And you see several of them already, actually. That is the command that applies, so that forces the execution of the intermediate Python code. So up to this point where the update pipeline is executed, I know that my pipeline is up to date. This brings me to a nice comment, actually, because we talked about HDF5 in that data set here. You know the concept of hyperslabs in HDF5 or in NetCDF, where you can extract, for example, a single plane of data out of a three-dimensional data set. So here I'm talking about HDF5 data set, and a hyperslab is, for example, a 2D plane. What happens in ParaView when you load that data? How would you do it? You would load the data, 3D, apply, apply, and you get a full 3D grid loaded in memory. This can be very heavy, but you only want to look at the boundary layer, the bottom plane, or maybe the middle plane, or what do I know? So what do you do next? You do an extract void, that's the volume of interest filter, and you select that particular plane in your 3D grid which you want. And you say apply, and you got your plane. Everything is good, but you have read a full 3D domain. You've wasted a lot of computation, and possibly you were forced into reading this on a multi-server allocation because the data was too big. If you write, now you write the Python script. The Python script executes, it creates the object reader, then it creates the object, the filter extract volume of interest, it reads the index of the plane you want, and only then it executes. ParaView is smart enough to say, hey, I only want to read my boundary layer. I pass this, the coordinates of my boundary layer grid plane, to the 3D reader, and the 3D reader only reads that particular plane, and you do this on your laptop instead of using the supercomputer. That's the big difference. This, unless you use the update pipeline command, which would force the 3D reading. So this is where you have to know your pipeline well. You have to know how it behaves. If your reader is capable of extracting only a single slice, your advantage is to let the Python script get built up without triggering, without forcing the execution, and only at the end, when everything is set up, you say, apply, it executes, it reads a single slice, your boundary layer, you print it, you're done. Okay? So we have two sorts of updates. Let me search for it, but I probably have. I'm probably using just one of them here. Yeah. I'll just write it like this for illustration. Yeah, more or less. Information. Those are the two different commands. The update pipeline information, the whatever object, update pipeline information only does the first pass. This morning we talked about 3 passes in pipeline, the metadata setup. So it's very lightweight, but it ensures that the correct default values are used. And then the update pipeline is the one that does the third step of the execution. It's the full pipeline execution. So if you encounter during batch mode execution some places in your pipeline where the data does not have the correct default values, it's because you're missing that update pipeline information thing, which is lightweight. You insert a couple of those, and it fixes a lot of problems in your pipeline. There, I'm really done with the answer to the question. All right. So who's going to give me big data to visualize next month? One of you good? Yeah, okay. Really, typically, the people with big data are climate. You guys know, you know who you are, climate, and then CFD, and then Astro, and then fluid dynamics, etc. Those are the big consumers of the resources. Okay. And not to mention the people doing gridless data, but SPH. I was going to show you a couple of videos of SPH. Perhaps we can finish up with this. I have here. So there is the index rendering video actually that I had mentioned earlier. Oh, this was just the screen capture of things. So we've seen that one already, but I wanted to show you the gearbox SM player gearbox. This is typical of an SPH calculation, no grids, just particles, and that thing I have done using the point Gaussian display that we talked about this morning. We see here just particles flowing through this particular device. Okay. I wanted to show you earlier the combustion video. At the coffee pause, I said that volume rendering with visit was extremely slow. This is one of them that took a long time to compute. What we see here on the left side, this volume rendering of the velocity magnitude. So it's possible, but it's really very compute heavy. Okay. And because it's compute heavy, there's no interactivity, which really makes you give up easily with volume rendering. If you don't have interactivity, it's nearly impossible to do a good job. So the availability of the NVIDIA index library now really opens up. It's recent, yeah. It's ParaView 5.5 will be the first version with it. The availability to do interactive volume rendering is going to open up, I think, a lot of possibility like this one.
I have one small question.
Yes.
As a user, why should I use Visit?
It's pretty simple. If you're doing, for example, plasma on a torus, we're getting very specific. In Visit, there's a set of modules that are implemented only on Visit for that particular requirement. They've been fine-tuned for a specific project in Visit. Here's another example. If you're using, you have lots of particles, and you are using the fast bit. Am I saying right? Fast bit, it's called, library to do multidimensional query and compression of your particle data. If you're using that, as far as I know, ParaView still does not have an interface to the fast bit library, so Visit would be your best choice. Visit has some remarkable filters to do a query-driven analysis with, I have an example that I've run for several tutorials in Visit. So tutorials that are more, not tutorials, algorithms which are really dedicated to large collection of transient data and query-based, query-driven analysis. ParaView is a little bit less strong on that. And then I could also give a list of advantages which are specific to ParaView. One of them is actually being ParaView makes much greater use of the GPU. So if you are rendering bound, then you really need to use ParaView. Now, the people of Visit for a long time, the developers of Visit for a long time have said visualization is not a rendering, what's the word? A rendering hungry process. The big consumers of compute time are the disk I/O, and then the filtering, the middle layer of your pipeline. So perhaps you need a bigger thread pool to execute that with a different execution engine, and the rendering itself is no big deal. Now, you need to differentiate two things in visualization. Visualization for interactive exploratory activities. You have a new data set. You need to understand that data set. So you don't know a priori what you're looking for. In that case, you want the fastest interactive pipeline as possible. You want to try new things, throw them away, try something else. You want a very quick interactive loop. If, however, you know exactly what you want, you've done that visualization multiple times, you've done the same computation last year, and now this is a new campaign, but your pipeline is ready, there's no interactivity, you're going to run batch mode only, then the need for interactivity and for interactive rendering is perhaps not as important, and you could do with several solutions. So it really depends on... I have another example of where would you, in my case, where I could only use visit is for a project which is using curvilinear AMR. AMR is adaptive mesh resolution, okay? You can do it with patch-based AMR, so rectangular grids, and you implement that in ParaView with VTK uniform grids. If, however, you have spherical shells which are refined, so it's a curvilinear AMR, you can only implement that in visit. End of the discussion. Yeah. So it's great. Life is great. We have two wonderful softwares, complementary. In some cases, visit will do better. In some cases, ParaView will do better. This is also a place where you need to consult me. I have experience with both, and I can possibly offer some suggestions on which one is more appropriate. Up until, well, still today it's true, but it's going to change very soon. Visit uses a pretty old VTK library. It uses VTK 6.1. ParaView uses VTK 8. Actually, it says 9 on my recent ParaView here. So it has the most recent development of VTK are integrated in ParaView. Now, on the mailing list of Visit, they said, as soon as the 2.13.1 release is done, we're going to merge over the VTK 8 branch. So they're finally going to get up with a really good, up-to-date VTK. And this, by the way, explains why in the last 2 days we've had some of you here for the in situ tutorial. We said Sensei build with libsim is not interchangeable with Sensei build with Catalyst. It's only for this reason, is that the levels of VTK are not yet equal. When this becomes a non-fact, you'll be able to switch, do a single computation of your Sensei apps and run with Catalyst or Visit. All right. I have a couple of slides I once made for pros and cons of the two applications. I could search for that slide somewhere in the millions of PowerPoints I have to document that better if you want. Very good. Wow, 5:03. I think we can officially close, and then I'm available here for coffee if there is more coffee to drink, or just a simple chat with you for a little bit. I thank you very much for your attention, for your patience with me. I promise I will finally put together all the slides and send you the PDF. By Monday morning, you'll have them. Okay? Thank you very much. Thank you.